Okay, well, thank you very much for sticking with me until the end. Well, it's not the end yet, right? There's still 2 hours to go here. But I would like to explain anyway today another application of the Dave-Joe steepest descent method. This is going to be connected with the Pendulum-2 equation and in particular these rational solutions that we discussed in lecture 1. And I guess what I want to say today is that you will see shadows of all of the things that we discussed yesterday in the orthogonal polynomial analysis. There are images of all of the tools that we've used in that lecture appearing here. But the key thing that's going to be different is that in this situation, as we vary the independent variable for the Pendulum equation in the complex plane, the jump contour, instead of being fixed on the real line, is going to have to move in the complex plane so that we can control the asymptotics. And that means that the g function that we use is not going to be quite as simple, but it will be much more interesting. And so I will explain that as we go. Okay. So in lecture 1, we showed how rational solutions of the Pendulum-2 equation with parameter m, complex number m here, can be generated iteratively using the Becklin transformation that we derived from the Riemann-Hilbert problem, but also was found by Lukashevich in a different way. And here is the formula. So we can get a solution of this equation where m is replaced by m hat, which is m plus 1, and we will call that modified solution p hat. And that can be obtained by a solution of this equation by this formula here, okay? And so the rational solutions are generated by starting with the simple solution that p is the zero function when m is the zero constant, and then turning the crank with this Becklin transformation over and over again, and that has the effect of incrementing the value of m by integers, okay? So we asserted also in lecture 1, but we didn't prove that rational solutions can only occur for integer values of m in this equation, and that for each such m, there's exactly one rational solution. But those are not so difficult to prove, so we can try that. So the first one, the Pendulum-2 equation admits a rational solution only if m is an integer. So, so we suppose to the contrary, m is not an integer, and suppose that p is still a rational solution of the differential equation. So in particular, m can't be 0, and so that means that the differential equation does not admit the 0 solution, and that means that the solution p of y being a rational function, it's got to have a Laurent expansion for large y that looks like this, okay, some integer power on the y variable, and this p0 is not equal to 0. So it's got some expansion of that form near y equals infinity. So then you plug this series into the differential equation, assuming that m is not 0, and then you find out quickly that because of some dominant balance in the terms, this n has to be minus 1, and the p0 coefficient has to be equal to m, okay? So therefore, you can do a residue computation. You can integrate around the circle of radius r, say, bigger than r, with counterclockwise orientation and divide by 2 pi I, and you will pick up exactly the coefficient p0, which is m, okay? But anyway, you could also try to consider that this p of y is a rational function, so you could compute this integral the other way, not using this expansion, but just by enumerating the residues at all the finite poles, right? And using the residue theorem on the inside of this curve. So if y0 is a finite pole of order n of p of y, well, then that number has to live inside of this circle of radius r, because this expansion is valid outside. And so we have a convergent Laurent series in the neighborhood of that point y0, like this. So this is the order of the pole, right, n, and then we have again some p0, p1, and so on, and this p0 should not be 0. So then you plug that into the differential equation, and you find out that the n has to be 1, so the pole has to be simple. And p0 squared also has to be 1, so the residue is either plus or minus 1, okay? So if you call n plus the number of poles with residue plus 1, and n minus the number of poles with residue minus 1 at finite points of the complex plane, then by the residue theorem on the other side and the interior of this circle, you get that this value has to be the difference, n plus minus n minus. There's a little typo here, which I have to fix, I guess. Okay, so that's a contradiction because we assumed that this number was equal to m, which was not an integer. Okay, so that's the reason why you can only have a rational solution if m is an integer number in the differential equation. Okay, so then here's something that was first proved by Murata. So suppose that m is an integer, then there's exactly one rational solution of differential equation 1. So in lecture 1, we used Lukashevich's Becklin transformation along with this kind of symmetry to get to negative values of m. Okay, we used this and Lukashevich to show that there exists at least one rational solution for every integer m. And when m is 0, then you know that p exactly 0 is one rational solution, okay? But if p is any other rational solution when m is equal to 0, then for some integer n and for some p naught different from 0, this is a non-zero expansion again, so p naught is non-zero, you've got this n over here, and you substitute this now into equation 1 under the assumption that m is 0, that's different than we had before, and now you discover that this n has to be 1/2. Okay, so that means that the p of y equals 0 is the only rational solution because you can't have a rational solution that behaves like a square root at infinity. Okay, so for m equals 0, we're done. But now you suppose that m is a non-zero integer and that p and p tilde are two rational solutions for that value of m. So what you can do is you can compose the Lukashevich formula with the symmetry that we indicated to change the sign of m, and that gives a different transformation that you can write down here explicitly. And here the effect is to decrement the value of m. So what's interesting is if you compose this one with the Lukashevich formula, then you can check that they are inverses to each other. Okay? So that means assuming that p is a solution of differential equation 1. So that means that these are these maps here, despite any appearances, they're actually invertible. They're 1-to-1. So therefore, if you repeatedly apply one or the other of them, depending on the sign of m, starting from these two solutions, p and p tilde, you're going to wind up with two other solutions at m equals 0, and those have to be the same. And by injectivity, that means that p and p tilde also have to be the same. Okay, so that's the proof that you can find like from Murata. Okay, so now I want to describe some special polynomials that show up because they're interesting. So let's consider this rational recurrence. So we start out with the function 1 and the function z, and then we can build the function, say, q2 from this formula by using q0 here and or q1 and q0 like that. Okay. So you try to iterate this thing, and it's clear you're putting in some expressions in the numerator with derivatives and squares, and then you're dividing, so this ought to be some rational function. But in fact, Kajawara and Oda showed that the qn given by this recurrence relation, you could express it as a constant multiple of some Wronskian, and that Wronskian involves only polynomial functions. And that means that despite whatever is going on when you look at this with division in this formula, somehow this fraction always turns out to be a polynomial in Z. And these polynomials are called the Yablonski-Vorobiev polynomials. They were actually discovered originally in the late 1950s. And they were shown to yield the unique rational solution of equation 1 in the form of sort of a logarithmic derivative of a fraction of the consecutive polynomials, and here you should just substitute the z variable is proportional to y in this way. Okay, so that's related to the scaling of our Painlevé 2 equation, the way we are writing it. Okay, so anyway, well, Fukutani and collaborators showed that all the roots of these polynomials are simple roots, and that qn of z has no roots in common with qn minus 1. So if you think about this formula, that tells you that all the roots are, all the poles of p of y are simple, and they have residue minus 1, plus or minus 1, depending on whether the 0 is in the numerator or the denominator. So all kinds of remarkable properties of the real roots of these Yablonski-Vorobiev polynomials have been studied by Peter Clarkson and a different Peter Raffelson in these references. Okay.
So
Yeah.
in correspond to the degree of Q?
No. So that's the degree of Q. I forgot how it's related, but it's not just n. Yeah, they're not like the orthogonal polynomials. Yeah. Mm-hmm. Do you remember? Huh?
They are related to n.
Yes, but I think he's asking whether the degree of Q sub n is equal to n, and I think it's bigger than n. It's like 3n or something like that. I don't remember offhand. Wait a minute, if that doesn't maybe.
N times n plus 1.
Yeah, there's. It's not 3n, obviously. Okay, but it's it's something that's not just n. Yeah. Okay. Well, so for each m in the integers, the unique rational solution p at p sub m, we'll call it p sub m of y. It's got simple poles with residues plus or minus 1, as we pointed out, and so therefore there's some rational function um of y that's such that pm is the log derivative of um. Okay, and so that's just by integration, really. And so we're going to normalize this um so that it behaves near y equals infinity, like minus 6 to the power minus m. So that's the constant there as far as y is concerned. And the functions um and pm, they actually show up in lots of interesting applications. The oldest one that I'm aware of is a physical application to steady electrolysis problems. This is the paper of Bass in 1960s, I think. Anyway, you can check the reference list. There's somehow the rational solutions of Pendulum 2 are supposed to parameterize some string theories, but I don't know very much about that. There's a reference for you. Then there's an interesting application you can read in this paper of Peter Clarkson, where the poles of the rational Pendulum solutions with opposite residues are meant to describe the locations in some equilibrium configuration of an ideal fluid of vortices with opposite vorticity. Okay, so plane equilibrium fluid vortex configurations. And then another one I'd like to tell you some more details about. This is some joint work with Robbie Buckingham. Involves universal wave patterns in the semi-classical sine-Gordon equation. So this is the sine-Gordon equation for some field capital U of x and t. And so what makes the problem semi-classical is to scale the derivatives with some small parameter epsilon squared like that. So the exponent just goes with the number of derivatives. That's the semi-classical scaling. And similarly for initial conditions, we're going to choose actually 0. It's a second order in time problem. So we specify the initial condition on u to be 0 and the initial condition on ut after this epsilon factor that's sort of going with this scaling, this semi-classical scaling, to be some fixed function g of x. Okay? And so epsilon is a positive parameter. The function g that's driving the dynamics is independent of epsilon, and one is interested to describe the solutions of this problem. So here's a sort of picture of what you get. So if you have this function g, which is kind of big in the middle of the like it is in this plot here, it's sort of larger in the middle. That g is like an impulse. You are kicking the function u at time 0 with some impulse, and somehow the way you need to think of the sine-Gordon equation is that it's describing the angle u of some pendulum that is located at position x. Okay, and the pendulum can have different angles as time varies and also as x varies. So what's going on in this part, you see this dark color, which corresponds to vertical configuration of pendulums. So what's happening is that the pendulums are rotating around in this part of the picture, and that means you've kicked the system quite hard there. But over here you see only this kind of bluish color, which is down here. So these pendulums are just doing this kind of motion, and that's because that function g is very small. So I picked some kind of a bell-shaped function for that g. So it's very small out in the wings, and there the pendulums are swinging like this. So you can see that there should be something interesting happening near these points here where the function g has just the right value that corresponds to the separatrix in the pendulum phase portrait. Okay? So that's exactly when you have the homoclinic orbit that connects the vertical configuration to itself, and that's happening right at this value of x. So anyway, so if you sort of blow it up, the picture, you see some kind of spaghetti like this. These kind of white curves are places where you have the downward configuration. And anyway, we would like to somehow describe that asymptotically as epsilon gets smaller and smaller. And you can see what the right scales turn out to be here. This is like epsilon to the 2/3, this scale. These little stripes have a scale of size epsilon, and the whole picture here should have some scale in time like epsilon log 1 over epsilon, okay? Anyway, so what makes the picture come out in this way turns out to be the fact that we are crossing with this function g, the pendulum separatrix, in a transversal fashion. And that means that if we take the derivative of g and evaluate it at this point x critical, that's not 0. So we can divide and multiply by 12 and get a number that's positive, as it happens, not 0, but positive here. And we'll call that number nu. And we can just do everything in terms of this constant nu. Delta x will just be the distance from this point, x critical. Okay, so then one of the results that we have with Rabi is this one. So fix an integer m and suppose that xt lives in a horizontal strip in the plane that's given by really this inequality on t only. Okay, so t is close to this value, proportional to epsilon log m, and quantized by this integer m by something which is half of this size. Okay, so we're tiling the xt plane with horizontal strips, and Sm is the strip that is given by this inequality here. And then we bound the distance from x critical by epsilon to the 2/3. So then as epsilon goes to 0, the cosine and sine of 1/2 of the function uxt are converging to this converging to these explicit formulas here. So there's some plus or minus signs, right, like this. This one involving, strangely, the Pendulum function um of y. But anyway, then there's a hyperbolic secant of t and hyperbolic tangent of capital T, and capital T is this combination of the variables. Okay, so anyway, the formulas look kind of simple enough in terms of this capital T, and if you think of capital T as just the time in this problem, then what this solution is representing is what's called the kink solution of the Sine-Gordon equation, and that's exactly this homoclinic orbit that connects the vertical configuration to itself. All the pendulums are doing this synchronously. That is the solution that's described if you think of this capital T as just time over epsilon. But that's not all that's in this capital T. There's other stuff here. There's a constant that has this parameter nu in it. And there's also this, okay? There's a correction term inside the arguments of this kink, log of absolute value of u sub m of y, okay? And that is one of these Pendulum functions. So somehow what we're saying is that the asymptotic formula for the solution of the Sine-Gordon equation is a series of kinks centered, the center being t equals 0, along some translates in time of the graphs of these minus log of absolute value um. So here's a plot of these graphs, okay? Here's a plot of the graphs, and the claim is that this is the theoretical version of this numerical picture here. So you can kind of see, right, that like this curve right there is this curve, okay? And so on. And if I were to make the epsilon smaller and smaller and be able to do better numerical simulations, this picture would look more and more like this one, the smaller the epsilon is getting, okay? So anyway, so that's quite an interesting result. One thing that you can observe here is that the pattern is not symmetrical left to right. Like there's, it's obvious in this picture and also here, I think, as well. So that should somehow be explained, and also to understand how this pattern develops as time increases. That's the index m, and so you've got to look at these functions um or the pm functions or something like that for larger and larger values of m, and that's motivating a sort of asymptotic study of these rational solutions of the Pendulum 2 equation. Okay, so that's how I got interested in this problem. It's because I was interested in this problem, and it just turned out that the solution of this problem led to these functions um of y. It was a surprise, okay, but very interesting to learn about, and then that led me into a different field that I've been working in for some couple of years now. All right, so so what about this asymmetry? Well, one thing to understand the asymmetry of those graphs is to think about what's going on in the complex plane of the y variable. And so if you go ahead and remember, you can get these recurrence, you can get these Yablonski and Vorobiev polynomials by just solving an explicit recurrence relation. Then using Mathematica, you can find symbolic formulas for these Pm of y's, or for the polynomials if you like, as long as m is not too big. If it gets too big, then the symbolic expressions just explode and the computer cannot hold them, and so you can't do any calculations. But anyway, if m is not terribly big, you can do it. And then you can ask Mathematica to find the poles by finding the roots of those Yablonski-Vorobiev polynomials. And here, this routine called NSolve is very handy if you use a big enough value of the parameter working precision. So we used 50 for these pictures. So here's just a plot in the complex plane of some dots. And this is the y-plane, and these dots are the poles of the Pendulum function p15 of y, and the red dots are the negative residue poles, -1 residue. The blue dots are the +1 residue poles. So they're sort of making a nice little pattern. There's also a black curve here that I'll explain later. It's sort of meant to draw your attention on those points. But anyway, there's a bunch of points, and they're forming this kind of regular pattern. But it's sort of triangle shaped. And the triangle, the real axis in the plot is here. So if you kind of cut this triangle through the real axis, then you see that somehow the points should not be symmetrical left to right. And there's some sort of reason that you might understand for how that could be, how the pictures that we showed on the last slide might not be left-right symmetrical. So anyway, so this is P15, okay? And then here is the same y-plane. Here is P30, and here is P60, okay? So very beautiful patterns that you're seeing. You clearly can see that there's some expanding triangle region here that's got all of the poles and zeros in. And inside of this region, although the dots made by the computer are kind of on top of each other because they're so dense, you can see that there's some kind of crystalline pattern of these dots that should be explained. Okay? So lots of interesting features. Also, there's fewer dots near the corners, and also, as it happens, near the edges. All those things can be explained as it happens. So that's the pictures of the poles and the zeros, which capture a lot of information. Okay. Yeah. Sorry?
Sum of residues.
The total sum of these residues is not 0 because there's the point at infinity that gives a residue. But yeah.
It's a fixed number, or?
Yeah, it's m.
Okay.
Yeah, the sum of the residues is m.
Oh, right. That's good.
Yeah, right, because it's yeah.
So these poles are in fact zeros of UM.
Yeah, one color dot here is the zeros of Qm, and the other ones are Qm minus 1, I think. Yeah.
But just now you said PM is UM prime over UM.
Yes, that's right.
And the UM is what kind of, they are not...
Okay, let's look. Right, so where was it here? Okay, here we go. Yeah, right. Right. So PM is the logarithmic derivative of this fraction. This fraction is it could be thought of up to a constant. This is u sub m. Yeah. Okay. Up to a constant. Disappears when you take the logarithmic derivative. Okay. Right, so that's the sort of, so we would like to have some explanation of these things, and the point is that, it's not a good idea to deal with this recurrence formula because m can't be made as big as you want. So anyway, so the poles, they appear to occupy a region of the y-plane that's expanding in size as m increases, and it turns out that the right scale is that y should be proportional to m to the 2/3 to capture the biggest poles in the complex plane. So here's what we're going to do. So given a fixed value x in the complex plane, let's look at p sub m for y in a small neighborhood of this point. So we're going to just look near a point x times m to the 2/3. So that's some point kind of that should be oriented relative to that triangle. And then let's use some kind of dominant balance considerations to check that the size of the neighborhood that we should look in should be proportional to m to the minus 1/3. And that turns out to also be a good fit for the scale of the spacing between the different poles, which is why when we make the pictures for bigger and bigger m, the poles get more and more dense, okay? So the spacing is like that. So it's going to 0. So anyway, so what we'll do, we'll write y, given this fixed number x, okay, we're going to write y as, okay, basically m to the 2/3 times x, I'll explain this half later on, plus, okay, m to the minus 1/3 times some other w, and this is defining a relationship between y and w that's just parametrized by this constant x that we were fixing, okay? So you think of it as like just make a change of the independent variable in the Pendulum equation between y and w. And so if you also scale the p function by basically m to the 1/3 and call this resulting object f, we can write what is the equation for f as a function of w. And it's just a straightforward substitution. This is the differential equation for f as a function of w. So you see that there's the second derivative term, a cubic term. X is a constant here. So this is a linear term that's constant coefficient. There's a constant term. And then there's this thing, which is sort of the complicated bit because it's got w there, which is the independent variable. So this is a non-autonomous term in the differential equation. But the whole thing is divided by basically m. And m is large, right? So we start thinking that we should just ignore this last term, and if you neglect it, and because you're neglecting it, you decide to put a dot on the f since it's some kind of approximation. So that's what I'm using. It doesn't mean derivative. Then this is somehow what we might guess as being the approximate differential equation for p sub m when m is large. And it's an autonomous second-order differential equation, cubic in unknown. So it's the kind of thing you might study in an undergraduate ODE course. You can draw the phase portrait, for instance, for this equation. Okay, so this autonomous model equation that we just wrote down, it's got two types of solutions. So the first ones are the equilibrium solutions, where the f dot function doesn't even depend on w. So this left-hand side is 0, and the right-hand side then has to also be 0. And if you clear things out a little bit, you find out that that this f naught should satisfy this cubic equation right here. Okay, so there's 3 possible equilibrium solutions, and then there are non-equilibrium solutions. So for those, we can, without any problem, we can multiply by f prime, and so we do that, and we integrate the equation. And then we have something that looks like this, and this pi here is just a constant of integration. Okay, so that's the equation for the non-equilibrium solutions. Well, anyway, so it turns out that for this equilibrium problem, the unique solution of this equilibrium cubic, which is parameterized by this number x that we are fixing, we are interested in the unique solution of this cubic that depends analytically on the parameter x for large x. And it looks like 1 over x plus smaller as x goes to infinity. So that function, you can check, it's very nice near infinity. It looks like 1 over x, but as you come into the finite part of the complex plane, you eventually run into some branching points. And there are 3 of those branching points. There's a point called x sub c, which is this exact negative number, and then there's the 2 rotates of that number by plus or minus 2 pi over 3 angle. Okay, so these 3 branching points, they appear to accurately correspond under this scaling. So remember, x is sort of the point about which we're exploring. This point, rather, is the point about which we're exploring in the y-plane. So if you scale that up by m to the 2/3, these values, they seem to match pretty well the 3 corners of that domain that contains the poles in the plots for large m. And also, this formal approximation that would come out of just taking this equilibrium solution, so that means you have m to the 1/3 times this equilibrium solution for the parameter given by this value of x here, this value of x, which is basically m to the 2/3 minus 2/3 times y, so this formula, as a function of y, this has no poles, right? This is something that's just given by the solution of this cubic equation. So anyway, so while this is not in any way a proof, it certainly suggests that this kind of equilibrium approximation might accurately describe P sub m in some exterior pole-free domain close to y equals infinity. It's just a guess, but it seems quite reasonable and perhaps consistent at least, okay?
That means what? Near y is infinity, there's the pole appears inside the...
Right, so exactly. So this formula does not predict any poles at all, okay? And we're basing this formula on choosing this f naught dot to be the particular solution of this cubic that's analytic for large enough x. X is this thing.
And
Okay.
y is complex.
Y is a complex variable here. Right. So it looks like this equilibrium approximation of the equilibrium solution of the approximating equation might be a good approximation for P sub m, at least for large enough y, like in the outside of that triangle region. Okay, but it has to be proved, of course. On the other hand, if you think about the non-equilibrium solutions, which satisfy this equation for some integration constant pi, well, those functions are elliptic functions because this is a quartic polynomial over here. So those are elliptic functions, parameterized by the x, which is a parameter, and the pi is another parameter. So there's two parameters there. And for each choice of those two numbers, f is an elliptic function up to a phase shift of the w variable because the equation is autonomous and first order. So anyway, so all such elliptic functions, they are doubly periodic in the complex w plane, and they're meromorphic. They have regular periodic lattices of poles. And this turns out to be consistent with how the Pm function of y behaves in the w plane. So we're now not using the y variable, but remember we've localized to some point based on this parameter x, and now we have a tiny neighborhood of that parameter, of that point, which is mapped out by this new independent variable w. So if we look in the w plane, which is where we expect to see an elliptic function, near a fixed point x, that's arranged so that this quantity is inside of the triangle, okay? So then, this is the w plane for example, x equals minus 3/2, for m equals 15. So you see some red and blue dots like we had before. This is sort of the part of the edge of that triangle, and so is this, okay? So you can kind of still see the boundary of the triangle there. But if I keep the x value the same, and I look in the same w plane, but make the m bigger, we're zooming in on that point, and so the boundary should fly away. And indeed, if we keep everything the same, but just change m from 15 to 30, now you can't see the boundary anymore. It's gone off out of the plot. It's the same plot range for the w variable, and moreover, these points are almost turning into something very regular. It looks like some kind of a lattice in 2 dimensions, which is what you would expect if there was in fact an elliptic function approximating this Panlevec function. So there's m equals 30, and here's m equals 60, and even more regular, okay? So at this point, you really could almost just connect these dots and make little hexagons, and it would be a perfect tiling of the plane by some parallelograms, and that's what you need to do in order to somehow have an elliptic function approximation. Okay, so it all looks quite consistent. So again, it suggests but does not prove that the local behavior of Pm of y in the region where the poles are might accurately be modeled by elliptic functions of w. But anyway, so this is just guesswork, really, and we need to justify everything, and also the guesswork leaves some important questions without answers, and some of those questions are that we don't know exactly where in the y-plane that we can say that the interior pole region stops and the exterior pole-free region begins, okay? We can kind of see it in the pictures, but how can we see what's going on and how to really predict where that's going to be? A related question is, what is the mathematical mechanism for the transition between those two regions? How does the function Pm of y know to change from poles to no poles, right? Another question, given an x value that corresponds to the interior of that triangle, how should the integration constant pi be picked, right? We integrated up some equation and picked up a new integration constant. How do we choose that properly? It should be determined somehow. And finally, given x and pi in the complex plane squared, C2, there's a one-parameter family of elliptic functions because it's an autonomous first-order equation for the elliptic function, of replacing w with w minus constant. So how should this phase shift w0 be determined, right? It's not obvious at all from our formal modeling. Okay. So all of these things have answers, and we can get those answers by thinking about the Riemann-Hilbert problem. So we'll come to that. But first I want to tell you about another scaling of the differential equation. So here's what we're going to do is we're going to actually wind up with a different Pendulum equation just coming from P2. And this has a name. This is called the Coalescence Cascade in Pendulum theory. So what I want to do is I want to zoom in on one of the corner points. So xc, remember, this negative number was the left corner of our triangle in the x coordinate. So I'm going to zoom in on that point by writing y is m to the 2/3 times the corner point plus a fluctuation here, okay? And the fluctuation now, instead of writing it in terms of w, I'm going to use t as the new independent variable. And now the scale is different, m to the minus 2/15, which looks weird, but that's the right number. And there's another constant, which is just for convenience here to make the equation come out nice. Okay, so then we may notice that this equilibrium solution at the corner point has exactly the value minus 6 to the negative 1/3. So we could look for fluctuations near that value by taking p sub m to be, okay, there was this overall factor m to the 1/3, there's our equilibrium solution, plus some fluctuation, and here the fluctuation should be measured by a size m to the minus 1/15, some constant for convenience, and we'll call the new dependent variable capital Y. So anyway, so if I take these and just plug in, this is a mapping little y to little t, this is a mapping p into capital Y, and I plug them into the Pendulum 2 equation, then we get an equation for this capital Y as a function of t, and that equation is just right here. Okay, so now there's again some term that has the m in it, but it's got a power m to the minus 2/5, and so that term we may think could be dropped in the limit m large, assuming that t and big Y are both bounded. And then you have these terms left over, and what those terms constitute, make up, is the Pendulum 1 differential equation. So Pendulum 2 has turned into Pendulum 1 by somehow formally rescaling the equation to zoom in on one of those corner points. Okay, so you should expect that maybe some solution of the Pendulum 1 equation should be a good approximation for the capital Y of t, and hence by unraveling this mapping, the original rational Pendulum function, about these kind of fluctuations of it anyway, about the equilibrium value close to the corner points. Okay, so I'll mention something about that at the end of the lecture. Yes.
How do you know that this exceeds by computation?
Yeah, so I mentioned that if you go back here and look at these equilibrium solutions, you solve this cubic equation for x large, right? Then you get something that behaves, one of the roots behaves like 1 over x. And I'm interested in the branch points for that. And so what I do is I just ask, where is there a double root? The branch points are the double roots. So there's a what's it called? A resultant that I can calculate. And the resultant explicitly tells me that there's 3 roots, 3 points in the complex plane, namely this one, and this one, corresponding to this value. So those, and then I just mentioned that those points, numerically, they seem to match the corners of the triangle. That all has to be proved, but if we just go with that, it seems reasonable to try to expand the equation near those points and see what's happening. Okay? All right.
This corner is the left-hand corner.
This is the left-hand corner, but there's the whole equation for PM has a e to the 2 pi I over 3 symmetry to it. So once you understand the left corner, you kind of get everything. Yeah. Mm-hmm. Okay. So anyway, so to prove, and in some cases to actually just properly formulate these and maybe some other results, we have to really generalize analyze some representation of PM of Y when M is large, and we're going to assume without any loss of generality that M is a positive integer here. So, there are these algebraic representations, determinant formulas of Kajiwara and Ota, Wronskian determinant formulas of Kajiwara and Ota. There's the iteration of the of the Yablonski-Vorobiev polynomials. All of these techniques can be used to find formulas. But the formulas just become more and more complex the larger m is. So it's a similar situation that we had with the orthogonal polynomials, where you can apply the Graham-Schmidt method, but that only gets you so far because the computation becomes more complicated the higher the degree of the polynomial that you wish to compute. So these formulas can be useful for finding some properties, like some interlacing properties of the roots or poles of the functions, or some symmetries, but they're just not so useful for trying to explain pictures of the sort that we have been plotting here, okay? And for those, we really have to make the m really big. So the neat thing is that the Riemann-Hilbert representation of Pm of y that we found in lecture 1 by applying this isomonodromy theory and the lax pair of Jimbo and Miwa, that's a problem that seems to have a similar complexity no matter what integer value you pick for m. The m is just a parameter in the jump conditions, actually in the normalization condition at infinity. That's it. So we're going to use that representation to prove rigorous results on large m asymptotics. And so let's recall that Riemann-Hilbert problem right now. So here are the Stokes matrices again for Painlevé 2 rationals. So the odd indexed Stokes matrices are lower triangular with I in the off-diagonal entry. The S2 and the S4 are upper triangular with I in the off-diagonal entry, and S6 is the only one that looks different. It has -1 on the diagonal and -I on the off-diagonal. Okay, and the contour sigma for the Riemann-Hilbert problem, it consists of 6 rays going out from the origin at these angles, so multiples of pi over 3. Okay, so the problem is to find a matrix Z with parameter m, not a power, just a parameter, Zm of zeta y for an integer m, 2 by 2 matrix that's analytic in the complement of this 6-ray contour. The matrix should extend continuously to the contour from each sector of the complement, taking continuous boundary values Zm plus, Zm minus on each outward-oriented ray, from the left for the plus and from the right for the minus index. And those boundary values should be related by this jump condition that involves the Stokes matrices conjugated by an exponential, and the exponential involves this exponent zeta cubed plus y times zeta. Y is the independent variable for Painlevé, and the only place that the m index shows up in the problem is in the normalization condition, because we expect that Zm of zeta y times this diagonal power matrix minus zeta to the power 1/2 minus m to the sigma 3, that product should tend to the identity as zeta goes to infinity. That's the Riemann-Hilbert problem that we wrote in lecture 1 for the Painlevé 2 rationals. And we're assuming here, you may remember that problem had an additional constant called kappa, a real constant kappa, and that constant kappa has been set to 0 because we said that we could do that without loss of generality. Okay. All right, so then if you solve that problem, then the Zm should have an expansion as zeta goes to infinity. So Zm times this power factor went to the identity matrix, but that means really it's identity plus something times 1 over zeta plus something times 1 over zeta squared, and those somethings will depend on the m, and they'll depend on the y, which are both parameters in this matrix. Okay. So from these expansion coefficients, we get the rational solution, Pm, of the Painlevé 2 equation from these coefficients by this explicit formula here. Okay. Sorry? Well, that we explained in lecture 1. Maybe I just will... we've already discussed that. Yeah, sorry. I want to go on. But we proved this formula in lecture 1. This one here. Okay, so anyway, we may observe that that Zm, if we evaluate the matrix function Zm at zeta star, y star, these are complex conjugations, and then we take the complex conjugate of the 4 elements of the matrix, this object solves Riemann-Hilbert problem 1 whenever Zm does. You can just check that. So then we remember that the Riemann-Hilbert problem under suitable conditions, which relates to the use of a Liouville theorem argument, only has one solution. So this problem only has one solution, and consequently this matrix and this matrix have to be equal to each other. And if you trace that through these expansions, that tells you that PM of y star is the same thing as PM of y star, okay, for every m in the integers. And similar arguments also show that you can rotate PM by 2 pi I over 3. So it's good enough to look only in the upper or lower half plane. It's also good enough to get things in just one of the sectors of opening angle 2 pi over 3. Everything else is obtained just by rotation. Okay. So anyway, so the Riemann-Hilbert conditions that define this matrix Zm, they're illustrated on this diagram here. So here's the jump contour, and here are the jump matrices for the problem on each of the 6 rays. And then we expect that this Zm should be normalized at infinity involving the parameter m in this way. Okay? All right. So as we mentioned, the only place where m enters into the conditions of the Riemann-Hilbert problem is in the normalization condition at infinity like this. And so it's looking at that, you see that the large thing, okay, this is, I was mentioning that there was an m minus a half showing up everywhere. Well, this is why, right? It's m minus a half is the large thing, actually. And so it's natural, actually, to consider the small parameter, epsilon, is just 1 over m minus a half. Okay, so we're going to write things going forward in terms of this small number, epsilon, which is the reciprocal of a half integer. Also, to make the problem more similar to the one that we studied in lecture 4, the Fokas-Itzkataya problem, we also want to have the large parameter 1 over epsilon showing up in the exponents of the jump matrix. And right now there's no m in the jump. So we can accomplish that by just scaling the variables of the problem. So this is already a natural thing. We already said that somehow the size of y is like m to the 2/3 to capture the triangle. So here we just get something of size 1, roughly speaking, by this product. Let's call that x. And over here we'll redefine a new spectral parameter z from zeta by a similar scaling. And then we'll define m as a matrix depending on z with parameters x and epsilon out of the Zm in this way. So we just replace the zeta with z in this way. The y is replaced with x in this slot. And then this is just a convenient normalizing factor. And it's a left multiplication, so it will not have any effect on the jump conditions. It will just modify the normalization at infinity. So then we also take advantage here of the fact that this contour sigma is invariant under this dilation scaling. So it's the same contour in the z-plane as it was in the zeta plane. And this constant prefactor is analytic, so it doesn't affect any jump conditions. So the jump contour and the jump conditions are preserved, but the only change is that everywhere that we had theta of zeta y, we just write out what that is in terms of these quantities, and that's 1 over epsilon now times theta, the same cubic, but now evaluated at z comma x. Okay? So we pick out a 1 over epsilon now in the exponents of our jump matrix. Also, the normalization condition looks the same now, written for m and z as it did for z and zeta. Okay? That's a consequence of using this factor on the left. Okay, so we have a sort of equivalent problem for m now, and we're going to study that Riemann-Hilbert problem for small epsilon, which means large little m. So just as in lecture 4, the first step is to introduce some kind of appropriate g function for the problem, and that g function should have a kind of dual purposes. So the main purpose, like in lecture 4, is to stabilize the jump matrix for the problem. So with the help of the g function, the modified Riemann-Hilbert problem has jump matrices that have good pointwise asymptotics as m goes to infinity, or equivalently epsilon goes to 0. And then there's an auxiliary purpose, which also was there in lecture 4, and that is renormalization. So for problems like the one we have in our hands that have a non-identity normalization as z goes to infinity, one of the purposes of having the g function in the problem is to result in an unknown that now tends to the identity matrix as z goes to infinity. So remember, in the Fokas-Itzkataya problem, we thought, well, that's where this sort of equilibrium measure comes into the game, we'll try to pick up probability measures so that we get something that looks like log z at infinity and so on, and that's how we're going to get rid of our non-identity normalization. Okay. So anyway, so after some initial deformations of the jump contour sigma that I'll explain later, we're going to look for a g function, g of z with parameter x, and the point here is it's independent of the small parameter epsilon. The same thing was true yesterday in lecture 4. Our g function built from the equilibrium measure had nothing to do with the capital N that was in the game, and that's one of the important features of it. But anyway, so this function g of zx has the property that it's analytic off the jump contour, and it satisfies that zx is like log, okay, now it's minus z plus small. This is not really terribly important, except that we have this jump matrix on S sub 6, which is going off in the positive real direction, and that's the one that doesn't have identity identity on the diagonal. It's got minus ones there. So there's some kind of a branch cut in the problem going off in the positive direction, and that's why I want to have log of minus z here. But anyway, let's take that to be the principal branch, and we're assuming here that the deformed contour sigma, which I have to explain to you, it's going to contain the positive real line for large enough z. So that's why this thing will have this thing's branch cut is exactly in that positive real line, and that's the place where I want the contour to be. Okay. All right. So then, now let's go ahead and do that. So we'll assume that we have such a g function, and let's introduce it into the problem by conjugation in this way. So m will be multiplied on the right by the usual factor, e to the minus g sigma 3 divided by epsilon, which is our small parameter. And then it's useful to also put in some constant independent of z, but depending on this parameter x here. So let's put this constant conjugation in like that. We'll determine that later. That's similar to, you may remember in lecture 4, there was this Lagrange multiplier that we called lowercase l, and we also did some conjugation with that, and that was just to get something to be 0 instead of another constant. This is playing a similar role, okay? So lambda is like the Lagrange multiplier. So anyway, so then this O function is analytic off the deformed contour sigma. It satisfies the proper normalization condition that O should go to the identity matrix as z goes to infinity. And then if on some arc of the deformed jump contour, we could write the jump condition for m in this form. So m plus is equal to m minus times some core jump matrix that we'll call V conjugated by the theta, right? So just like that. So if that's the case, then we can write down right away what the jump for O looks like, and it's this formula. So the corresponding jump for O plus equals O minus. So here are the elements of V, okay? And then there's a function H plus minus H minus and H plus H minus plus lambda showing up. And this function H is just this quantity. So it's got the G function in it, and it also has the sort of built-in phase or exponent in our Riemann-Hilbert problem, 1/2 theta of z comma x. So this is a function that's analytic exactly where G is, but now we have the boundary values of that function appearing in the jump matrix, okay? All right, so that's similar to what we had yesterday, except our matrix is more complicated. It has 4 entries generally, and we had an upper triangular matrix in the last lecture. Okay, so to stabilize the jump condition for O in the limit when epsilon goes to 0, what we want to do is somehow partition the deformation of the contour sigma that I still have to explain into some arcs. And on each one of these arcs, we either want to have that h plus minus h minus is a constant function of z, okay? Or perhaps on some other arcs, I want that h plus h minus is a constant function of z. So those are exactly analogs of our variational conditions that we wrote down in the last lecture, just written in terms of this function h. So in other words, from here you can see that h prime squared, okay, so the prime is going to kill the constant in every case, because the prime means derivative with respect to z. And so if I take h prime squared, it doesn't matter whether I have a plus or a minus here. That's something that should not have any jump discontinuity across any arc, of our deformed contour. So then being as g should be a bounded function to avoid introducing any singularities that we don't want in the matrix O. And because theta is this cubic, z cubed plus xz, that's an entire function, then this tells you that in fact h prime of zx squared has itself to be an entire function. And you can write out the asymptotic behavior. So here is h prime squared is exactly this expression. This is the derivative of our cubic with respect to z. So that's these terms here. And then the g prime, that's something because g was supposed to behave like log of minus z at infinity, g prime has to be 1 over z plus smaller terms as z goes to infinity. So that quantity squared, which we can write out up to constant terms like this, that's the behavior as z goes to infinity. And so by Liouville's theorem, since this is an entire function and this is its large z asymptotic expansion, h prime squared has got to be a polynomial. Namely, it's got to be this polynomial where this pi is just this order 1 term. It's the constant term. Okay? That pi might depend on x somehow, but anyway, whatever. So that's the expression. Okay, so this relation that we just obtained on h prime, okay, this is called the spectral curve for the problem. And what I think is really fascinating is to compare this spectral curve relation that we got from Riemann-Hilbert considerations to this differential equation that we got by just, formally scaling the Pendulum equation. Because you'll notice that the thing on the right-hand side up to this factor 9/4 is the same quartic polynomial in both cases, okay? And even though from some point of view it's kind of a coincidence here, it's a coincidence that happens again and again and again in the study of Pendulum equations, not just Pendulum 2, and not just rational solutions, actually. So it's showing up all over the place, this kind of notion of a spectral curve in Riemann-Hilbert theory, and then a limiting differential equation from the sort of Pendulum point of view. Anyway, so ultimately it's this coincidence, I'll still call it a coincidence, that leads to the fact that Pm of y can be approximated by elliptic functions that satisfy this differential equation here. So we'll see how that works later on. Okay. Well, anyway, so what's up with this quartic? This is the quartic here. X is a complex variable in our problem. It's a parameter, and then there's this pi, which is just floating around as another integration constant. So this thing can have different configuration of roots depending on the values of x and pi in C2. So here's maybe the most degenerate thing is you could have a triple root z equals a, and then a simple root z equals b for the quartic. So 3 plus 1 equals 4. So let's consider this identity. Let's write this quartic polynomial as z minus a cubed times z minus b, and get some relations between a, b, and x and pi. So we just compare the coefficients. So these 4 equations have to hold true that should relate a and b with x and pi. So there are exactly 3 solutions of this problem. So let's let omega be a cube root of unity. So then x is minus this number times omega, a is this number times 1 over omega, and b is this number times 1 over omega. And moreover, the integration constant pi has to be exactly a cubed times b, whatever these numbers are. So this case corresponds only, as it happens, look at this x value, it's only the 3 corner points in the complex plane. And it should be regarded as quite special, but maybe useful for some analysis of those corner points. So that's what's happening. So near the corner points in the plane, this cubic has to degenerate into, this quartic has to degenerate into a cubic factor and a linear factor. That's what's happening, but only at those points. Okay, another configuration, you could have 2 simple roots, z equals a and b, and then a double root, z equals c. So let's again write out the polynomial, the quartic, as a product of z minus a times z minus b times z minus c squared, and match the coefficients, and now you get these 4 equations here. And so for every point x in the complex plane, you find out that you can eliminate the a and the b, and you discover that c has to be a solution of the equilibrium cubic equation, okay, that we've seen before with this f0 dot as the variable. And then A and B are determined up to a permutation in terms of the C and the value of X by these quadratic relations here, okay? So moreover, the pi, the value of this constant pi, has got to also be written in terms of X and the solution of the cubic C by this formula like that. So this configuration doesn't have to only work at certain values of X, like the corners. This can happen for any X in the complex plane. So it's a completely general case. We don't get any information about X, but given an X in the complex plane, we could try to use this kind of configuration of the spectral curve to solve the Riemann-Hilbert problem. It's an option that we have. Okay, and it involves this kind of equilibrium solution of the approximating differential equation as it happens. Coincidence. Okay. You could also have a configuration just with 4 simple roots, all of them unequal. So now we compare the quartic on this side with the expression in terms of the product of factors over here, and now we have 4 equations on A, B, C, and D. And we can regard A, B, C, and D as being determined up to some discrete symmetries by X and pi in C2. And so this is also a general case. There's 4 equations and 4 unknowns here. So pi is not determined as a function of X, which is different than it was in the last general case. But later on, we're going to impose some additional conditions to actually fix the pi as a function of X. And then that will help us to solve this problem in terms of elliptic functions. Okay, so that's it. So there's only those 3, and there are no additional consistent configurations of roots, so you can check that. So for instance, we can't have 2 distinct double roots for any pair pi, X and pi in C2. So either you have a triple root and a simple root, those are the 3 corners. You have a double root and 2 simple roots. That could happen anywhere in the complex plane. And then you could have 4 distinct roots. Again, that could happen anywhere in the complex plane, but you also don't know what this pi is in that case. All right. So let's tentatively, let's think about the simplest general configuration. That's the one that involves the C that solves the equilibrium cubic, okay? So let's suppose tentatively that C is defined near x equals infinity as the analytic root of the equilibrium cubic that behaves like 1 over x as x goes to infinity. And then we determine A and B as functions of x up to permutation from these quadratic relations here. Okay, so that's some quadratic formulas if you want. And then you're going to take h prime of zx squared to be exactly that quartic, which in this case is the product of a quadratic factor and 2 linear factors. Okay, so A, B, and C, they may be considered as analytic functions in some domain near infinity, and actually you can continue them analytically to the complement of a contour that looks like this. So here are the 3 corner points of the triangle in the x-plane, and we can connect them with some branch cuts that meet at the origin like that. So in the complement of this domain, of this contour, we can define A, B, and C as analytic functions of x from that cubic equation and the quadratic formula. So we take those, okay, and for each such point x in the complement of that triangle, of that 3-segment contour, suppose that sigma AB is just some oriented arc from A of x to B of x, and we're going to define a sort of version of the square root, which we've seen yesterday already. This function r stands for root, okay? It's a function of z that depends parametrically on x that's determined by these conditions. So it's some kind of a square root of z minus a times z minus b, but it's supposed to be analytic in the complex plane, take away this oriented arc from A to B, so that's the branch cut, and it should behave like z as z tends to infinity. So those 3 things determine the function r of zx. And so now I'm taking a square root and recalling that h prime behaves in this way as z tends to infinity, then we get this formula. So h prime of zx is exactly 3/2 z minus c of x times this square root function. That's it, okay? It's an elementary formula. And then from h prime, we get g prime by putting in this 1/2 theta prime, like that, and subtracting the h prime. So this is the formula for g prime. And so then we use the equations satisfied by A, B, and C, and you can check that even though this formula looks like G prime goes like Z squared at infinity, there's lots of cancellation here. And when you expand everything out, in fact, G prime is 1 over Z plus small, and that's exactly what we need to get our logarithm when we integrate. So if we take L to be some contour that connects Z equals B with Z equals infinity, that's disjoint from sigma AB, then we can define g of zx by integration like this. So here, this is just a logarithm that's got its branch cut on this curve L that goes from b to infinity. So that's the logarithm term. And then we can integrate infinity to z, this quantity here, and this thing will be independent of path in the domain that's indicated over here. Okay? So g prime is just given by this explicit formula right there when we do the integration. So now we know g of z. So then we can easily check that g and h are analytic functions for z in the complement of our sigma AB contour and this line L that goes from b to infinity. The sum of the boundary values of h, that's equal on that branch cut on this sigma AB to a constant, which we'll call minus lambda of x. It's an analytic function of x in the indicated domain with those three lines omitted, those three segments omitted. And then on this contour L that goes from b to infinity, the difference of the boundary values of h is exactly 2 pi I, and that's again sort of coming from the logarithm. So also, if we assume that L agrees with the positive real axis for z large enough, then we expand that integral out, and gzx is log of minus z plus smaller terms as z goes to infinity, and this has its cut exactly on the positive real line, as it should. It's the principal branch. Okay, so those are all the properties that we kind of wanted to build in, and so now I want to sort of try to explain how we're going to deform this contour that I sort of ignored at the beginning. And the way we're going to understand that is we're going to look at the signature charts in the complex plane for the real part of the function 2h plus lambda. And I just want to mention we know what this function 2h is, and we can compute this constant lambda. So it turns out that the function real part of this thing is a single valued function in the complex plane, take away the branch cut, sigma AB. So I'm going to sort of show you what these curves look like in the complex plane. This is the z-plane, and this is just where the parameter x lives. So I'm going to start out, I'm going to show you what's happening on these black dots, but let's take this pink one first. This is a positive real value of x that's big enough. And now this is the z-plane, and the plus and minus signs are just the signs of this quantity here. Okay, so there's A, and there's B, and there's a dotted line here. The dotted line is the branch cut sigma AB, okay? And then actually the dashed line. The dots are the axes. Okay, so the signs are indicating exactly what's happening. There's a change of sign that happens across that branch cut, and there are also sign changes that happen in other parts of the complex plane. There are curves emanating from A and B with these angles that you can see separated by 2 pi over 3, and those are locally giving us 3 different basins where there are 2 different signs, and then the branch cut is giving us an additional sign change in the vicinity of B, for instance. So that's the signature chart for this pink value, and then we can look at this one, and there's some kind of rotation as it has occurred, and now, in fact, the branch cut coincides also with this zero level curve of the real part of 2h plus lambda, like that in this case. Then we can look at this one, and this one, and this one, and this one. So that's sort of, you can make plots and try to get some feeling for what these regions look like. But what I want to say about it really is that we can then use these regions to try to figure out where to put the jump contour. And the reason, yeah. Okay. Yes.
So around A, now you only have 3 regions.
Yeah. So whoops. Okay. So there's minus on both sides of this curve, and what that's saying is that so actually the real part is the real part of 2h plus lambda is continuous across this curve and has the same sign. So it's like a river valley for the real part. Okay, that's what's happening along this curve. It's simultaneously a zero level of this function, and it's also the branch cut. And that's why we have minuses on both sides. But in the first plot over here, there's in this case there are three smooth level curves coming out where there are sign changes. You see a sign, minus plus, plus minus, minus plus. And then there's this branch cut here. And here in this picture, 2h plus lambda has got a jump discontinuity across this vertical line between A and B where the sign changes. Okay? And what happens when we move from the first plot to the second is that branch cut coincides with the level curve. And so now instead of having a jump discontinuity, we just have a zero level, and it's like the absolute value of distance from the curve. Yeah.
So you are fixing x and then look at the.
Right. So this plot over here is showing an x value as. Huh?
The z is a complex number.
Z is the complex number, so we're in the complex z plane, and for each z in the complex plane, I ask what is the sign of this quantity here, right? Which is a plus or minus. This is the real part of some analytic function. Okay? So, or in other words, the black curves are the zero level curves of this nice function of two variables, okay? And except the function has got some kind of a corner along this curve here. That's why we don't see the branch cut there. But the picture changes depending on x, and so when x moved from this pink dot over here, at this pink dot I have this picture, and now I will move to this x value and the picture will change like that, and so on. But really, the picture is continuously deforming. I can only show you finitely many frames here, but the picture is deforming in a continuous fashion. Yeah. So anyway, the point is that this quantity, 2h plus lambda, that is the thing that is showing up in the exponents now of our Riemann-Hilbert problem. And so I want to somehow arrange the contours, the jump contours, so that if I have 2h plus lambda as my exponent, I am in one of these minus regions. And if I have minus 2h plus lambda, then I want to be in the plus regions. And in each case, because of the sign on the picture, the exponential term will be decaying to zero as epsilon goes to zero. Okay? That's what I want to arrange. So I have some slides to show you that, so let me go to that. So here is how we'll do it. So let's take this point over here, okay? So that was the case. Now you see the grayed out curves are the plot, right, that we had maybe before. There's A and B. The dashed line is that sigma AB branch cut, and then we have the signs written on here, okay? So the original jump contour is this 6-ray black thing, and I want to now deform it so as to be helpful, so that this picture is helpful to me. So the first thing that we can do is to sort of push the contour up to pass through A over here and to pass through B over here, okay? So now I've got that there's an arc of the jump contour which is just in the minus valley over here, which is going to help a lot. And this arc is in the plus valley. Okay, so that's good. What's the next step? So now we will move this contour down so that it's in the plus valley, and this one has been moved into the minus valley, and that means I've had to glue together two arcs along here and here. So that means I have a product of two jumps that are happening at the same curve, but that's easy to calculate, so now we know what's happening along these two curves, and we have good asymptotics now for our jump matrix here and here. Okay, next I peel off something like this to pass to infinity in this valley, like that. So that's combining one of these curves with the thing that was going out before. Now I'm going to do a similar thing down here, like that. I pull him off like that, and now this one is going to infinity. So this is a good place for this curve. It's a minus region. This curve wants to be in the plus region, so that's where I put it. And then we have this piece left over, and this one I'm just going to connect with some smooth curve like that. And at the end, you see this kind of gray dashed line here was our original branch cut. But in the end, having done this, I'm going to now make that branch cut coincide with this curve between A and B, like that. So it will become dashed, and that's the plot that I want to use now. So having done that, sort of gone through those steps, that's the deformation part, okay? I've just moved these jump contours around in the complex plane, And since the jumps themselves are analytic functions, that's something I can do for free, provided I take into account how things are multiplying together on this central part here. So some neat things have happened. We have this curve in the plus region, this is in the minus, and this one's in the plus, and something like that is also happening over here. And the only one that's kind of ambiguous is this dashed curve here, because this was a minus region, and this is a plus region down there. So let me show you what has happened. Yeah.
Middle dash line lies on the same sheet.
So the middle dashed line is actually on the branch cut now. So that means that the function r does not have a well-defined value. The function g does not have a well-defined value on this curve anymore. But it doesn't matter. It doesn't matter because we've done some multiplication of jump matrices through these several steps. And if we look at the product of those jump matrices, it turns out that these boundary values no longer show up. Let me show you the picture, okay? So this is the jump matrix computed now on this new jump contour. So the part in the middle here, this is where the jump for the square root is coming up, and the jump matrix is just a constant, 0, -I, 0. There's no dependence on z at all in that thing, and so I don't have to worry about whether I'm on this side or that side or whatever. It's perfectly okay to have the branch cut right on that curve. The jump doesn't see the branch cut, okay? However, all the other matrices here are now really great because you see there's identity matrix plus something off diagonal, and the off diagonal is either exponential of plus or minus 2h plus lambda divided by a small positive number epsilon. So in the case of the minus rather, I'm in the plus domain, and that means that this is going to be exponentially decaying to 0 when epsilon goes to 0. This one also will be exponentially decaying because now I have the plus sign, but I'm in the minus region. Okay? So this is similar to our lens opening, is what it is, from lecture 4. Remember we did that opening of the lens. This is sort of the Pendulum version of opening of the lenses. Okay? So anyway, so we've introduced the G function. These are the jump conditions for this matrix O at this point. And as we said now, the G function has done its job for us because we have exponential decay, except right in the neighborhood of these points. And there's also a constant jump along this curve here. So there, if I take the limit epsilon to 0 pointwise on the jump contour, all I'm going to see is this. And of course, the asymptotics of that jump matrix going with epsilon going to 0 are not uniform near these 2 points. So it's a similar situation now that we were in when we got to the matrix D in lecture 4. We now can try to model this matrix by solving this jump on this curve between A and B, and then doing something local near these points that should be based on Airy functions. Okay? It's the same thing. So yeah, so the G function has done its job. All the jump matrices tend to the identity uniformly and exponentially fast as epsilon goes to 0, except in a neighborhood of this curve, this dashed curve between A and B, and there we have this constant jump condition. So this motivates that we should define an outer parametrics, just like we did in lecture 4. So we're going to solve these jump conditions in closed form. So we'll define a function, now I'm going to call it beta of zx, that's analytic away from that dashed curve between A and B, and its fourth power should be z minus A divided by z minus B, and it should tend to 1 at infinity. So this defines what the function beta is, because its branch cut is exactly that curve between A and B. It's some kind of 1/4 root of this quantity, and the thing it determines which branch we should pick is this value. Okay? So beta is a well-defined function. It's some kind of 4th root of this fraction. So then we just build the outer parametrics. This is actually the same formula in terms of beta that we had in lecture 4. So this thing solves exactly this jump condition. Okay? And the thing that's wrong with it is that, if anything, is that because it has beta and 1 over beta in the matrix elements, it blows up like a 1/4 power at both A and B. And that's the same thing that happened to us yesterday about this time. So as in lecture 4, we have to use some kind of inner parametrices, and they are, just as before, they're constructed out of array functions, and those will be used in some neighborhoods of A and B. And so using a combination of some conformal maps that are defined from this function h near A and B and some array functions, we're going to get some matrices that we will call O dot A and O dot B. And these are designed to satisfy the jump conditions for O exactly in neighborhoods of A and B. They have unit determinant, and they're going to match nicely onto the outer parametrics in the sense that if I fix some radius, the distance from the point A, for instance, right, and I look at this ratio, O dot A to O dot out inverse, I'm going to have identity plus something small, this small, actually, as epsilon goes to 0. And a similar statement is going to hold for O dot B on a small circle centered at Z equals B. So that's the matching condition. All right, so those are analogs of what we did in lecture 4, but first we had to deform the contour into some kind of curved thing, and then we could use all of those same ideas. Okay, so the global parametrics is just written by the piecewise formula, A and B inner parametrices in these disks near A and B, and the outer parametrics everywhere else. And so then the corresponding error in the problem is defined in the same way that we had in lecture 4. We just compare the matrix O, which we don't know, but which solves a Riemann-Hilbert problem whose properties we know. And we compare that matrix O with this parametrics O dot inverse. O dot is this matrix, so we know all of these things. This way written on the last slide, and these we can write explicit formulas for. So the jump contour for the matrix E is shown here. So we have these curves coming out of A and B. The dashed part that we had before between A and B has disappeared, and that's because these two matrices solve exactly the same jump condition on that dashed curve. Also, all of the arcs inside of these circles have disappeared, and that's because these matrices here solve exactly the same jump conditions that this matrix solves inside of those two disks. This is exactly as it was in the case of the orthogonal polynomials. So all that remains are these arcs outside the disks, and there we have uniform exponential decay of the jump matrix for O to the identity. And we have these circles where we have to jump between the outer and the inner parametrices, and there we have said that there's a good match between the outer and the inner parametrices. So what that means is that we can check that we have a small norm Riemann-Hilbert problem for this error matrix E. So in particular, we can conclude that E of Zx epsilon is identity plus E1 over Z plus E2 over Z squared and so on as Z goes to infinity. And all of these coefficients, these matrix coefficients, E1, E2, and so on, they are O epsilon in size, okay? So what that means is that you can now remember that you've got the solution of the small norm problem about which you have estimates, and then that thing can be used to write explicitly what the original matrix M was by explicit substitutions. So actually here's the matrix Zm of zeta y, and it is written explicitly in this way for large enough Z. And so from there, we remember that, oh yeah, we can get the rational P2 function from peeling off some suitable coefficients in this expansion. So all we have to do is expand out these things. This thing we have explicitly. This one has estimates on its coefficients. And so in the end, I'm just going to jump to the result. In the end, what comes out of that is that m to the minus 1/3 times the rational Painlevé function is equal to c of x plus small as m goes to infinity. And this c of x is the thing that solves that equilibrium cubic. It's the distinguished root of it that behaves like 1 over x for large x. So we have proven this asymptotic formula using Riemann-Hilbert theory, but actually we have to keep something in mind. So the result that I just told you about, it hinges crucially on our ability to deform the jump contour sigma for the matrix M to take advantage of the sign chart for the real part of 2h plus lambda. And our ability to do that, in turn, depends on the topology of the zero level curve of this function. So what happens is that there's a transition in that zero level curve. A topological transition happens when the double root c of x moves on to the zero level curve. So I would like to illustrate that here. So here is the x-plane with some dots, okay? And here is the z-plane where I illustrate the zero level curves, and I'm trying to put our jump contour on top of the picture. So the black curves are the jump contour deformed, and the gray ones are the zero level curve for the function 2h plus lambda. And all of this corresponds to this pink dot, which was one of the dots that we had in our plot the last time. So now I'm going to move that pink dot to the boundary. This will become pink, and the picture will change. So here the picture has changed into this one. And what I want to point out is that there are two gray curves that are crossing each other now. So just compare. You'll notice that the black curve was passing through a kind of narrow channel here. And what's going to happen is that when we move into the boundary, that channel will close up. So there, it is closed, okay? You see that right there, the channel has closed. And at this point, in order to stay in the plus region, this black curve has got to pass right over that saddle point at just the right angle, and then I can continue in the plus region. But this is going to make some contribution to the solution of the Riemann-Hilbert problem, because I do not have exponential decay in the neighborhood of this point anymore. Okay, so something is happening at this edge, and once I pass inside, now that sort of isthmus has opened up the other way, and now you'll notice that there's no way for me to go from A to infinity in this direction to stay in the plus region. I've got to somehow build a bridge over this minus or something like that, because there's a minus region in between, and this pink part of the contour, I can no longer control the exponents in our Riemann-Hilbert problem. Okay, so a topological change in the level curve happens when this C moves on to the zero level curve, and that's happening, right at this spot, which looks like it's on the boundary of our triangle. Okay, so what I'm trying to say is that as long as we are in this exterior region, then we can make the deformation so that our contour is in the right parts of the sign chart. And if I somehow try to pull in x too close to the origin, then I have a situation like this, and there's no way for me to orient these contours on this picture so as to obtain the exponential decay that I need in order to get that formula to be true. Okay? So in order for that to be a theorem, somehow there's a condition on x, like x should be outside of this triangle. Then we have that result. So we conclude that this formula here is valid if big X, if little x, absolute value is so big that this point c of x is never on the level curve of this zero level curve of this function. So that means that we may say that the inner boundary of this exterior domain is given by the equation that the c of x is on that level curve. And if you write down what this means, it's some condition on x. It's a real condition on a complex variable x. So it's a system of curves in the complex x-plane. And it turns out that there are some curves that emanate from these corners, but they are harmless topological transitions, so we're not going to plot those. But then there's this curve, and this curve, and this curve. And those are exactly given by solving this equation, okay? That's where those come from. So this is the explanation in the Riemann-Hilbert world of these bounding curves of this pole region. Somehow they're bounding the triangular region. Actually, you can check that it's not a triangle. Using this equation, you can show that the interior angle at each corner point is exactly 2 pi over 5 radians. So it can't be an exact triangle, but it's some kind of a curved triangle. Okay.
We try to avoid the stationary point by adding some more constraint. Can you explain the pink region?
Oh, this one here. This pink region here?
So how
Right, so-
to remove the
Well, so I sort of said something like, this is like the ocean over here, and I need to stay on the land in order to control the exponents, right? So what I have to do is I have to build a bridge somehow. I have to construct a causeway across this water so that I can well, I'm not going to be able to stay above the water, but I will be able to stay exactly at the 0 level. Okay? So in other words, I have to do something to modify what the 0 level curve looks like. And what that modification is to go to this, less degenerated version of the spectral curve where I have 4 distinct roots of the quartic equation. That's the case we haven't used yet. And I'm going to use that now in order to build the bridge. Okay? Okay, so for points inside of this triangle T, let's call that triangle region T, we can try to use the other general configuration where the spectral curve corresponds to this equation. So I'm going to now use capital letters, capital H in place of little h, capital G in place of little g, and so on, because it's a different g function. So I want to use different letters, but it's the same idea. So capital H prime squared was this quartic, and now I'm going to write the quartic as a product of distinct roots, a, b, c, d, and then we know that there are certain relations that should determine a, b, c, and d in terms of x and pi, right, these two things. So the spectral curve corresponds to this kind of quadratic quartic equation like that, and for distinct roots, this curve gamma has got genus 1. So in order for the steepest descent method to work in this kind of more complicated situation, we have to restrict attention to a special type of spectral curve, of genus 1 spectral curve, and that special type is called a Boutroux curve. So Boutroux curves, they satisfy the additional conditions that if I have this genus 1 curve, there's a homology basis of 2 cycles, we'll call them A and B, 2 non-contractible independent closed loops on the Riemann surface. So we have to insist that the differential rho dz has got 0 real parts for its integrals on the basis AB of cycles. That's what's going to define the curve gamma as being a Boutroux curve. So these conditions will show up exactly in our Riemann-Hilbert analysis. That's why we're imposing them. But they have some kind of nice algebra geometric interpretation, I think. And these are called Boutroux conditions that define a Boutroux curve gamma. Okay, so let's recall that for the genus 1 configuration, this constant pi in the complex numbers, which you may think of as R2, it's not determined a priori. It was free, which was annoying. But now we have these Boutroux curve conditions, and those are 2 real equations, which is exactly the right number that we would need to determine this pi as a function of x on the triangle. So to start out, we could just guess a solution of these Boutroux equations from some symmetry. So when x is equal to 0, which is the most symmetrical point in our whole picture, we can check that these values here, so A, B, C, and D, these are consistent with the necessary conditions, which are just coming from matching the coefficients, right? And also with pi being the product of the 4 roots, we get that pi of 0 is exactly 0. And that allows us to check that gamma, this gamma with these endpoints here, these branch points, is a Boutroux curve. We can just check that the integrals are both purely imaginary. Okay. So then we need to somehow continue that solution to hopefully the rest of the triangle. So we just apply the implicit function theorem. And so some simple calculations that I'm not showing you here will compute the Jacobian of this system of equations on A, B, C, and D. And the Jacobian, taking into account those Boutroux conditions, is proportional by some non-zero constant to this expression here. So it's the imaginary part of the product of an integral over A dz over rho, which is the square root of our quartic. And here's the integral over B, the other homology cycle, dz over the square root of the quartic, complex conjugate. Okay, so now this differential, 1 over rho dz, that's the holomorphic differential as it happens on gamma, and it's the unique one up to scaling. For a genus 1 curve, there's only one holomorphic differential up to scaling, and so it's like a principle of classical algebraic geometry that this expression here is finite and non-zero as long as the curve gamma is non-degenerate, and that means that A, B, C, and D are distinct complex numbers. The roots of the quartic are distinct complex numbers. So this is obviously true when x is 0, because we wrote A, B, C, and D right here. These are 4 distinct numbers, okay? And so what it means is that we can continue the solution to a small neighborhood of x equals 0 and get a Boutroux curve gamma with branch points A, B, C, and D. And moreover, we can continue the solution to larger x until 2 or more roots coincide, because that's the only place where the Jacobian can have a problem. And this condition, that 2 or more roots coincide, is what determines the interior boundary of the triangle T. So the exterior boundary of the triangle was where the C moves on to the 0 level curve. The interior boundary is where 2 or more roots coalesce after being continued using this Jacobian here. And then it's not hard to show that the interior boundary coincides with the exterior boundary. So these are exactly the same thing, and this triangle that you see in the plots is exactly the transition boundary between the sort of genus 0 region, which is exterior, and the genus 1 region, which is the interior of that triangle. Okay, so this is the proof of that, but I think I will skip it. Okay, so to use the Boutroux curve defined on the triangle for steepest descent analysis, what we're going to do, yeah.
Outside region is genus 0.
The exterior region is genus 0 because there were the radical had a double root and 2 distinct roots. So if you ignore the double root, it's really a singularity, but let's factor that off. Then we have the square root of a quadratic for the 2 distinct roots, and that's a genus 0 curve. So to use the Boutroux curve for steepest descent, let's write the independent Painlevé variable y in the form epsilon to the minus 2/3 x naught plus epsilon to the 1/3 times w. So this was kind of like what we had at the beginning, defining w and y as being related to each other given some x naught, okay? And so let's write it like this for variables x naught in the triangle, inside the interior of the triangle, and w in the complex plane. So we're going to use the value of this x naught to define distinct branch points A, B, C, and D by the Boutroux conditions. But what I want to say is that we're going to think of x naught and w as independent parameters here. And the thing is, it's clear that if you know what y and m are, you cannot uniquely determine both x naught and w. So it means that we're going to have sort of multiple formulas for the same Painlevé function. Okay, and these formulas will all be asymptotically equivalent, but it will be handy for us because we can use different formulas that depend differently on x naught and w in order to accomplish to interpret some features of the asymptotic. So for instance, we can interpret x naught as some sort of coordinate on T considered as a manifold, a curved manifold. And dependence on x naught is going to characterize the slow variation of the parameters of our elliptic function as y moves through the triangle. So it turns out that these branching points, A, B, C, and D, they're smooth, but they're non-analytic functions of x naught. And so this approximation, if we try to view P as a function of x naught, it's not an analytic function. Okay, but nonetheless, it's capturing the way that those parallelograms of the elliptic function are deforming as we move through the triangle. So we're going to call x naught a macroscopic coordinate because it's giving us the slow variation of these elliptic functions. On the other hand, w, that we can think of that, if we like, as a coordinate on the tangent space to the triangle at the point x naught. And what we're going to do is show that our approximate formula is actually an elliptic function of w for every point x naught in the triangle. So we'll think of w as a kind of microscopic coordinate that gives us the fluctuation in all the poles as a sort of uniform lattice that's nailed to the point x naught in the triangle. And if you change to a different x naught in the triangle, you have a different uniform lattice of poles. Okay, so that's the idea. Well, anyway, let's introduce a different capital square root function that's got its branch points at A, B, C, and D. And so it's cut except on some contour that consists of an arc connecting C with A, C with B, and C with D. That's what this contour is. And R should behave like z squared at infinity. So in other words, this function R is defined on one sheet of the Boutroux curve gamma. And the branch cuts for that sheet will be this curve sigma ABCD. So then since h of zx naught is 1/2 theta minus g, and that quantity has a derivative that satisfies the spectral curve equation, then we get that h prime has to be exactly 3/2 times r. Okay, so that's it, it's just the square root really up to a 3/2 factor. So if we integrate up this equation using the boundary condition that g of infinity should be 0, I think this is actually, this should be g prime at infinity is 1 over z plus small is what it should read. I'll fix that later. Anyway, that defines g and h as analytic functions. For z in the complex plane, take away this sigma ABCD contour, the branch cuts, and also this sort of logarithmic contour that joins d to infinity and agrees with the positive real line for large z, okay? Okay. All right. So h plus h minus is, as it happens, constant on each arc of this branch cut contour. And on CD, the constant will be denoted minus capital lambda of x naught. So unlike little lambda of x, this thing turns out to not be an analytic function of x naught, but it's a smooth complex valued function of the real and imaginary parts of x naught. So some signature charts for this quantity real part of 2h plus capital lambda, well, they will vary depending on how x naught varies within the triangle. So let's look at some of those. This is the picture in the z-plane corresponding to the origin in the x naught plane. So here is the system of branch cuts now for my genus 1 curve, here, here, and here. And the other curves are the zero level curves of this function 2h, real part of 2h plus lambda. Okay? So, by the way, so this, Dershi, this is like the bridge that I wanted to build. It's now there, okay? So that's the picture of the origin. So the interesting thing maybe is that this picture is maybe a little bit simpler than the picture outside. It varies in a simpler way as I move these dots around. So let's look at that one down here. So it's a deformation of the original picture, but just a small one really. And qualitatively, it's quite similar. Okay, so that's the idea. So now I would like to place the jump contour for this matrix M of z and x naught plus epsilon w epsilon. I want to place its jump contour relative to the sign chart of this quantity, which somehow only involves the x naught part of our variable y. So for this dot over here, we have the gray curves that you can sort of see in the background there. And I'm going to place our 6-ray jump contour as illustrated here, okay? So some of these curves are exactly in these minus regions, and then some of them are kind of asymptotically in the plus regions, but there's little arcs which are dashed here, and those dashed arcs are the branch cut for the problem. So now we're passing in 3 ways over bridges, if you like. And hopefully we'll be able to control things there and there and there using the fact that these are branch cuts for our function. Okay, so anyway, as in lecture 4, we're going to open up lenses about these 3 arcs based on some factorizations. So in lecture 4, we used this sort of upper triangular is lower twist lower factorization, and this is exactly the analog in the present context of that factorization. And this is like the transpose of that thing. Okay, so we have also some upper triangular matrix, and we're going to factor it in this way. Okay, so now the idea is like on this one here, I'm going to take the jump that was on this contour, I'm going to factor it according to this rule into something that ends up on this boundary of a lens, something that ends up on this boundary of a lens, and there will be the central factor left in the middle, like that. And I'm going to do that also over here and also over here. So these lenses, there are 3 of them, and they're now kind of squished onto each other in some way. So it looks like I've just drawn a closed curve here through the points A, B, and D. But that's kind of, there's really a lens here, and another lens over there. Okay. So opening up those lenses, that's an explicit transformation from M to a matrix that I will call N of x naught plus epsilon w epsilon. And now we introduce the g function by this formula. So again, we call this matrix O of z x naught w epsilon. It's got, again, this kind of conjugation by the Lagrange multiplier, which is now the capital lambda variable, or function, constant, okay? Then there's the g function factor, and then there's the matrix N, which had just the deformation of the contour and the opening of the lenses. So we may observe that while m and n depend on the combination of variable x naught plus epsilon w, which is proportional to y, the matrix O depends independently on x naught and w, because we're using functions of x naught only to conjugate this matrix n that depends on the combination. So now the matrix O tends to the identity as z goes to infinity, and the jump conditions that it satisfies are summarized in this series of plots. So what I'm going to show you is just this curve is the jump contour, and I'm going to show you by the pink curves, okay, on these pink curves in the z-plane, this is the jump condition for the problem. And now you'll notice that there's a minus sign here. There's an exponent which lives in the plus region in both cases, so that is exponentially small. There's also this e to the minus wz coming out, and that's because we have this extra dependence on w in the matrix n, which is somehow not compensated by the g function and these constant conjugating factors, okay? So that just comes along for the ride, but we're going to use that in order to get elliptic functions in a minute. So, okay, so this looks exponentially small. That seems quite good. On this jump contour here in the plus region, I again have a minus sign on the exponent. Here there's two different boundary values of h from above and below, but the boundary value turns out to not matter because 1 over epsilon is a half integer, okay? So that's why that doesn't matter. On these three arcs here, which are all in the minus domain, now I have a plus sign on the exponent. So again, exponentially small contribution out here for bounded w. Okay, on all of these arcs around this circle and also these three here, I have this kind of a matrix. Now everything that you can see is in a minus region. And because we're in the minus region and we have the positive exponent, again, that will all decay away to 0. So the only things that are really left are these three dashed lines here. On this dashed line, I have exactly this jump condition that it depends on z and w by this combination here. This one, I've got an additional constant showing up, which is a real constant, this phi plus. And what that is basically the value of one of those Boutroux integrals, okay? So phi plus is one of those things. It's a smooth but not analytic function of x naught in the triangle. And down here, it's a similar story involving a phi minus, okay? So three different jumps that have simple dependence on z through these exponentials plus or minus wz. And otherwise, there's some constants coming from the Boutroux conditions. And there's basically 1, 2, 3 jumps that I have to worry about. I'm also going to have to install some airy parametrices at the points A, B, C, and D because of some non-uniformity reasons, exactly as in the last case and exactly as in lecture 4. So I'm not going to do that. But anyway, the point is that the g function, capital G now, has done its work. And a parametrics can be constructed from an outer parametrics that satisfies the jump conditions just on this branch cut, these three pieces, sigma, A, B, C, D, with minimally singular behavior at the branch points and identity asymptotics as z goes to infinity. And then we will need 4 airy parametrices near A, B, C, and D. And I just would like to mention that this part, the construction of the outer parametrics, this is like a multiple interval problem for the orthogonal polynomials because the curve here is genus 1. So we will need elliptic functions or genus 1 theta functions in order to solve for that outer parametrics. It's a little bit more complicated, but Luby is an expert in this sort of higher genus situation. So you can just ask her about it. Okay, so anyway, so the point is that the error, O times O dot inverse, is going to satisfy the condition of a small norm Riemann-Hilbert problem in the limit epsilon goes to 0, provided that the w is bounded because there were these factors e to the w z in the exponential, in the jump matrix that would have to be bounded, and w also has to be bounded away from any points where it might happen that the outer parametrics is undefined. That turns out to happen in this problem. Those are the poles in the w plane of an elliptic function that depends parametrically on this point x in the triangle. So when we build the outer parametrics, we run into a problem. There's a denominator which can have zeros. And that denominator is providing us approximate locations of these poles of the Pendulum function in the complex plane. So the outer parametrics can be explicitly written in terms of Jacobi theta functions for the Boutroux curve gamma of x naught. And so an approximation p dot of x naught w and parametrically depending on epsilon of this pm of y can be extracted from the expansion of this outer parametrics exactly in the same way as before. So p dot is written in terms of these coefficients by this formula here. And so rather than write down what this formula looks like, which is requires some tricks from algebraic geometry that are too detailed for us to go into in these lectures, but you can check this reference here. Instead, let's just go ahead and prove this result. So we're going to prove that this formula, okay, this approximate formula for our Pendulum function satisfies this differential equation, okay, with respect to w for fixed x naught in t and epsilon positive. So this is exactly our elliptic function differential equation. X naught is a constant parameter, and this pi, instead of being free, is now tied to x naught by the Boutroux conditions. Okay? So now these are just functions of x naught only, and we have this quartic polynomial on the right and the square of the derivative on the left. That's an elliptic function equation. So let's show that this strange looking thing solves that differential equation. That's going to tell us that our approximation is an elliptic function. Okay, so first, let's suppress all the fixed parameters, x naught and epsilon, in the proof to make the writing a little bit shorter. So then, so the matrix F, which is defined as O dot, this is the parametrics, the outer parametrics, times e to the minus wz sigma 3 over 2. Well, what this does is it just removes those exponentials depending on wz from the jump condition. So it has jump matrices that don't depend on w, and that means that dwf times f inverse has no jump discontinuities, and it's got sufficiently mild singularities that they're in fact removable. So it's got to be an entire function of z. And if you use the expansion of O dot out for large z, then you can check what this function is in terms of the coefficient O dot 1 of w. So that was the one, O dot 1 is just the coefficient of 1 over z in the expansion, okay? So going back to O dot out from f, from this formula over here, gives us a differential equation. So this outer parametrics solves a differential equation with respect to w, and it's written in terms of O dot out, of course, and also this coefficient in the expansion of O dot out, the 1 over z coefficient. Okay, so then similar arguments also show that this function g, which is just the square root function, times O dot out, sigma 3 O dot out inverse. That's an entire function, similar argument. So it has no jumps anywhere in the finite plane, and then you expand it out for large z, and you find out using this expansion of R and the expansion of O dot out that we had on the last slide, that this g is a quadratic. It's a quadratic matrix polynomial, so the leading term is sigma 3 z squared, and then there's a z coefficient and a constant term, all written in terms of these expansion coefficients, O dot 1 and O dot 2, and the value of x naught. Okay. So that's a quadratic. So now the definition of g, you can rewrite it if you want in this way. So g O dot out is equal to O dot out times R sigma 3. And what that says is that O dot out is just an eigenvector matrix for this matrix quadratic polynomial, and the eigenvalues of this matrix polynomial are just R plus and minus R of z. Okay, and also if you square the definition of g and you use that sigma 3 squared is the identity, then you get that g squared is R squared times identity, and R squared of course is the quartic right there times identity. So g squared, even though g is a matrix, g squared is really a scalar, and it's exactly the quartic that shows up in our differential equation. And so we're aiming for that. We're going to try to get there using this g. Okay, so from the Laurent expansions of this identity for g, and then also the Laurent expansion of O, for large z, we get a closed system of differential equations on these coefficients O dot 1 and O dot 2. So now the O has disappeared, the G is gone, and we just have a closed system on O dot 1 and O dot 2, okay, with respect to W. Now the quantity that we're interested in, this P dot out, that's built out of the O dot 1 and the O dot 2. Maybe I'll remind you of that formula here, right? So this is the thing we're looking at, those elements. Okay, so one way to write that combination is to write it as a diagonal matrix with something I don't care about in the 2-2 entry and P dot in the 1-1 entry. And that can be written in terms of the diagonal and off-diagonal pieces of O dot 1 and O dot 2 by this formula here. Okay? So now what we're going to do is use the differential equations on O dot 1 and O dot 2 to get this identity. So the derivative with respect to W of this diagonal matrix is just G of D squared. And remember, G of D squared, that's a scalar, right? So that's just this quantity here, and that's exactly in the 1-1 entry, the differential equation that we wanted to prove for our approximate formula for the rational P2 function.
Is it bracket here?
No, because this is a diagonal matrix, and this is a constant scalar times diagonal matrix. So, yeah. Okay, so this has really just been kind of an introduction to the type of results that you can get by the Riemann-Hilbert method on this problem. So some other results are the following. So you can get detailed approximate locations of the poles of Pm of y obtained as a regular lattice in the W plane that varies from point to point in the triangle, varying with this exploration parameter x naught that's moving around, the macroscopic variable moving around in the triangle. So for each x naught, there's a lattice of poles. Those are very accurate approximations of the poles of the Pm function. Also, there's an explicit formula in terms of elliptic integrals for the density of poles as a function of x naught in T. So if you're only concerned about sort of how many poles are there in some domain inside of that triangle in the limit when epsilon goes to 0, there's a formula that you can get in terms of elliptic integrals. In a similar way, the thing about a function with simple poles is that you can integrate it in 2 dimensions. And the integral is finite, right? The simple pole is integrable in 2D. So that means that you could do things like multiply your Pendulum function by a test function and integrate over the support of that test function and ask what's the limit as epsilon goes to 0. And that's something that you might consider as a local average or a weak limit of Pm of y near a point of the triangle. And those also have explicit formulae in terms of elliptic integrals. Okay, what about, this is all describing sort of the exterior, the solution of this cubic, equilibrium cubic, the interior, some kind of elliptic functions with poles that we can predict. What about the boundaries? So there are the edges of the triangle and the corners. If you approach any point of the boundary of the triangle that's not a corner, so one of these smooth edge points, then what happens is that your elliptic function degenerates into a trigonometric function. So actually, you're going to get poles that are not forming a 2-dimensional lattice, but instead they're forming a line in the complex plane. And then there's several of these lines kind of parallel to each other, but at some large distance in the microscopic coordinate. That's describing the behavior near the edge. So that's, you can read about in reference 6. And then I mentioned this degeneration of Pendulum equations when we picked a corner point and sort of zoomed in on the corner point. And that turns out you can also prove. So it turns out if you take this Pm of y, subtract off the equilibrium value at the corner, and rescale appropriately, then this converges as epsilon goes to 0 or m goes to infinity to a function y of t, where capital Y, where t rather is related to little y by this formula here. This is the same thing that we wrote earlier in the talk. And xc is the left corner point of the triangle. But now we discover that this function y of t is not any old solution of the Pendulum 1 equation. It's the so-called real tree trunquet solution of the Pendulum 1 equation. And that's like the unique solution that has no poles in some really huge sector of the complex plane. And guess what? That sector is matching exactly onto the exterior part near the corner where there are no poles, right? And so everything else is in this pole sector. That's the triangle part, and that's where the tree trunk K has its poles. So that's also in this reference 6. Okay, so all of these results, they've been obtained in some joint work with Buckingham, and we're using, as just to remind you, the Jimbo-Miwa formulation of the Pendulum-2 equation, and these are the references for those asymptotic results. But I want to tell you that there's another approach to this problem that Bertola and Botner advanced, and here's the reference there. So this uses, in my opinion, a mysterious identity to connect the Yablonski-Vorobiev polynomials to some Hankel determinants. Actually, there's lots of such formulas in the literature, but they have so far not been useful for analysis until Bertola and Botner produced a new Hankel determinant identity that had not been seen before in the literature. And I cannot tell from their paper how to get it, and I've asked Bertola and Botner how to get it, and they've not been able to convince me. It's just a mystery. I mean, you can prove it, but I don't know how you figure it out. I just don't know. But anyway, that's why I'm saying it's mysterious. But once you have it, then you have a way to analyze these Yablonski-Vorobiev polynomials. And what they did through their identity is they linked them to certain pseudo-orthogonal polynomials, meaning that we can apply Riemann-Hilbert methods just exactly like from lecture 4 to the problem. On the other hand, okay, so that allows them to reproduce some of the results we just mentioned in a different way, but the price you have to pay for going to this orthogonal polynomial picture is that you have to have many cuts of or many support intervals of your equilibrium measure. So many that the curve that's behind their analysis has genus 2, whereas in this Jimbo-Miwa theory, you see that only genus 1 curves show up. So somehow they have to do some gymnastics to figure out what's happening there. But in the end, using these higher genus theta functions, they're able to reproduce some of the formulas. Now, it also turns out that the Bertola-Botner Riemann-Hilbert problem, this one with the pseudo-orthogonal polynomials, you can also transform it, after a little bit of effort, into the Flaschke-Newell Riemann-Hilbert problem for Pendulum-2. They didn't notice that in their paper, but you can read about it in this review article here. Okay, so that's sort of taking us back to this alternate representation of Pendulum-2 by Flaschke and Newell. You can also get the results from that, but it seems that it's harder to get them than it is from the Jimbo-Miwa approach. Okay, so thank you very much for your attention for 10 hours and your interest in these lectures. And I have some references for you on these slides. So, but anyway, several references. So, thanks.
What's the 12?
Sorry? 12?
Oh.
Yeah.
Okay, thank you very much.
Any questions or comments?
Can I give a summary of what you're doing? You are interested in the Pendulum rational solutions for Pendulum 2. So this is the PM.
Right.
And using the Riemann-Hilbert method on the isomonodromy linear system, so this PM appears as a parameter in that system. And in the formulation of the Riemann-Hilbert problem is on the second term of your normalization condition.
The first two pieces, anyway. Yeah.
So you want to use the so-called steepest descent method to understand this PM.
Right.
And somehow during the steepest descent, this exponential term is critical in the analysis.
Absolutely.
So the zeros of the real part of H
2h plus lambda
X is critical.
Right.
And then on the poles of the, so you have that triangle, and outside the triangle you have a special case where H has a double zero.
H prime has a double zero,
H
right?
prime has a double zero. And the inside H prime has distinct zeros. And so you use...
Sorry, H prime squared.
Separate treatment to understand...
That's correct.
Steepest descent,
Yeah.
and then combine them up and understand the asymptotic.
That's right. Yep.
Thank you very much.
You know, I should also mention, you did ask me to mention some open problems. So I have one open problem that I could mention, and that is that, you know, if you make this triangle, so we have an asymptotic formula that's accurate in this center. We call this the bulk region sometimes. And then there's the exterior. There's also regions I mentioned around the edges here. So there's an edge region, and there's a formula that's valid there. And then there's another formula here that's the corner. Okay. And so that's very nice, and it seems to give the complete picture. But actually, the different regions in which these formulas are true don't overlap with each other. There are very thin gaps, actually, that separate these different regions where there's no formula for the solution of the problem. And what's a little bit annoying is that the formulas for the exterior and the edge, they agree somehow, and the edge and the interior, they agree, and the edge and the corner, and they all agree with each other. So we're not expecting that there's somehow a change in the asymptotic behavior, but there's no proof of that because we can't get the Riemann-Hilbert analysis to overlap in these regions. So these are kind of four distinct regions of the complex plane that don't actually overlap with each other. There are thin regions that are omitted. And it would be very interesting to figure out how to make the method work or some other method to give results in those regions.
What's sugar orthogonal polynomial?
It means that it's exactly the Riemann-Hilbert problem of Fokas, Itz, and Kitaev, except that the weight need not be a positive quantity. It might be defined on a curve in the complex plane, so instead of the real line. So in Bertola-Botner's case, the curve is a circle in the complex plane, and the weight is just some complex valued function on the circle. And what that means is that it's possible that those pseudo-orthogonal polynomials may not even exist, actually, because the Gram-Schmidt procedure requires some positive definiteness, and all that's coming from the fact that the weight is positive and you're dealing with the real line. So as soon as you're in the complex plane, that all bets are off, and the denominator in your Hankel formula can have zeros, and those are, of course, corresponding to like the poles of the Painlevé function. Yeah.
And also, Bertola and Botner, they also use Riemann method?
Yes, that's right. They analyzed this Fokas-Itz-Kitaev problem that corresponds to their pseudo-orthogonal polynomials. So it's kind of like lecture 4, but on a curve in the plane. And then the thing that happens to them in the course of their analysis is that their spectral curve has higher genus than ours does. Their spectral curve has genus 2 as its maximum, and that means that they have to get the results in the triangle, they have to deal with genus 2 curves and do some kind of reduction. So it's sort of like you have to do more work at that level. Whereas in the Jimbo Miwa picture, its maximum genus is always 1.